All right, I think we can get started again. So when we left off, we were talking about the third body reactions and how different collision partners can actually change the rate, but they only change the rate in the region where the pressure's low. When the pressure gets high, all of the partners collapse together to give you the rate, which is the transition state theory rate, the same as what we computed before. So transition state theory is assuming that you have a Boltzmann distribution, and that's implicitly assuming that your collision with the thermal bath is fast. That's why you have a Boltzmann distribution. And so at high pressure, that'll be true, that the thermal contact with the thermal bath is good because you have a very high pressure, lots of collisions. And so at high pressure, all the different bath gases, these guys will all come together and give some rate coefficient that's the same regardless of the bath gas. But at low pressures, you're affected by this phenomenon that you can have a significant amount of the collisions not be reactive because they're exothermic, but there's no way to give up the heat. And so they need collisions to give up the heat. You have to give it up fast enough to match the rate at which the reactions are happening. And so if your pressure is too low, it's like the reacting molecules are too insulated, and they can't give up their heat, and they're way far from Boltzmann. And that's what slows it down. You can make this nice plot of all the different bath gases together, and in theory, it should all match exactly in this line. It's not exactly like that, but you basically make a curve where you just divide the k by k infinity, so it's going to go to 1. And so all of them will go to 1 when you get to the Boltzmann limit, which is thermalized. And then the low pressure behavior mostly all comes together too. So TROA, let me erase something here. So if you want to really understand this in detail, you have the A plus B are coming together, and they're going to form AB. So this is the product, A plus B. And there's a Boltzmann distribution of the energies of the incoming A and B molecules as they come to collide with each other. So there's like a probability of their energy. This is like probability. This is the energy. This thing is a plot of energy, energy versus this coordinate in the x-axis is like the geometries of what these geometries are here where A and B are far away from each other, and then here's geometries where A and B are chemically bonded to make a new molecule. So for example, H plus O2. A is H, B is O2. You make HO2, HOO. Okay. So when these guys come together, they come in with one specific energy. So you have an ensemble of A's and B's, A and B collisions. They each have different energies. And so you have, say, a pretty good probability that you have about this much energy. But you also have a tail of some of them have energies like this, and some are cooler and have energies like this. So you have a whole distribution of possible energies that they come in at. And the ones that come in with very high energies, these are the ones that are really likely to come right back out because they would have to lose a lot of energy to get down below the asymptote. So if they don't lose enough energy, they're still be above the dissociation limit, and they're just going to fall apart on the way back out. The ones that come in with energies close to the dissociation limit only need to suffer a 1 weak collision is enough to give up enough energy that now they're trapped in the well, and they won't be able to come out. Is that all right? When you want to do the analysis carefully, you really should put all these intermediate energy levels in. There's a lot of energy levels of AB. you should put them all into your analysis and consider that the collisions could take this guy down to here, or they could take them down to here. And they have different probabilities depending on the collider, how much energy it's going to take away on average. And you could also have sometimes it takes more than average and sometimes less than average. So you have a whole distribution of possible amounts of energy you could lose. And each has an energy of how fast they come in and a probability of how much they come in. So Troa did the mathematical analysis of this whole system where you consider all these probabilities correctly. And that's how he came up with his formulas, which looks a lot like Lindemann's formula, except he has a correction factor. And the correction factor is by considering all these widths, the widths of the distribution of energy here, the widths of distributions of how much energy is lost per collision, and the fact that you have a lot of energy levels of A and B. And that gives us amazingly complicated looking formula here for this fudge factor F, the Troa factor. But actually it comes straight from the math, just he's really good at algebra. And so he was able to figure out this form. And when you match it against the experiment, it's like perfect. So for this system, we really understand exactly what's happening. And it's kind of what Lindemann said 100 years ago, but he's not quite right because he didn't worry about all these effects. And when you can worry about everything, you get this whole thing here. And you get a few extra parameters, but basically it's not much. Now, you do get really goofball cases sometimes. So one of them is HO2 plus HO2. This is also a super important reaction. So as we said, at high pressures and lower temperatures, when the H and O2 react, so now this is H plus O2, making HO2. At high enough pressures, these guys collide, and basically they just go down. And also at low enough temperatures, when they're at low temperatures, this distribution is very narrow. It's all down here, and it doesn't take much for them to go down. And so at low temperatures or high pressures, mostly H plus O2 just goes to HOO. But in our systems, we have a lot of H atoms, and we have plenty of oxygen because we're burning stuff from the air. And so this is a very, very important reaction, and you make a lot of HO2. Now, if I draw this a little bit better scale, up here somewhere is another limit, which is O plus OH. So when the H plus O2 comes in, if it came in at very high temperatures, so the Boltzmann distribution had a lot of guys up here, these guys, when they come in, are actually above the dissociation limit to the second thing. OH plus O, and this is the one that's going to make chain branching. So at very high temperatures, and particularly also at low pressure, so none of these guys collide during the way, they'll just go sailing right in and go sail right back out as OH plus O. And that's the most important reaction in combustion. So you have this weird competition where the pressure is driving it down, and lower temperatures are driving down, and higher temperatures and lower pressures are making it go that way instead. And that branching is extremely important because you want to know what fraction of your H atoms basically get consumed to go to HOO versus what fraction generate more radicals and make more H atoms. Very important for explosions. Now, at the lower temperature, higher pressure end, you make mostly it goes this way to HOO, and you can accumulate huge amounts of HOO, and particularly pre-ignition. So if you mix some fuel and air, and it's warm, but it's not quite hot enough to explode, you'll start making tons and tons of HOO because you're hot enough that you're making some radicals, but when you make the H atoms, most of them go this way instead of going this way. And this is like the pre-ignition condition, right before it's about to ignite. This is what's happening. And then these HOOs accumulate, and what's really important is what happens to them. And a very common thing is that two of them get together, and one of them extracts an H from the other, and you make HOOH, hydrogen peroxide, plus O2. And this stuff accumulates in pretty high concentrations right before the ignition moment. So when something's just about to ignite, you have a lot of H2O2. And so this rate coefficient also, you become sensitive to it in that temperature region. So this is typically like maybe 900 Kelvin, 1,000 Kelvin, 850 Kelvin, around that region. You have a lot of this reaction happening, and it really significantly affects what happens. And so people care, and what they saw was like this was like a perfectly sensible reaction with a normal kind of Arrhenius plot. But then when you get down low enough, the rate doesn't keep going down. It doesn't keep going down, down, down. It kind of gets flat and maybe even turns around, where the rate goes back up again at lower temperature. So this is super low temperature. This is room temperature. This is even lower than room temperature. So this is quite bizarre and caused a lot of confusion. And this reaction is also important in the atmosphere in smog, because HO2 is made by radical reactions in the smog. And so it was quite important what happens there in the smog as well. So people were really interested in the low temperature end as well as the high temperature end. And this region right around here is the pre-ignition region we really care about, around 1,000 Kelvin. So what is going on? So one possibility is there's just experimental mistakes. And so that was like Burke's conclusion. Hard to determine which of the rates are reliable. So that's one thing. And part of it is there's really not many measurements right in this gap, right around here. So not so clear what's happened. And then another part of this is, why is it doing this? And the theory is that at low enough temperature, these two guys can hydrogen bond, because the OH is a really good hydrogen bond donor. And this has a nice oxygen and really wants to accept a hydrogen bond. So maybe they're hydrogen bonding and making kind of a complex. And then maybe there's some way that that complex can do tunneling or some kind of rearrangement at low temperature and make the product and kick out the O2. I would say this is also kind of speculative, and people aren't really sure what's happening. So this is like kind of important stuff. And then for sure, this is true that the hydrogen peroxide, once you form it, it also is a third body reaction to make two OHs. And so you're in fall off again. You need high pressure to make this reaction run as fast as it could. This is quite important also for ignition. So for example, the ignition in a piston of an engine at maybe 30 bars is really different than in a low pressure bulb apparatus that we might do a vacuum experiment. And that can be confusing too. TROA studied, a lot of people studied this already to try to figure out what's happening. You can try to run it reverse, so take the two OHs and react them. And so OH is easy to probe by laser-induced fluorescence. And so people tried flash photolysis to do that. However, when two OHs come together, they can recombine to make H2O2, but they can also do other things. For example, this O can abstract this H and make water plus O atom. And so you have a complicated experiment because you have quite a few things happening at the same time. And so it's not so clear. And again, this is one of these ones where you need an absolute concentration measurement because you're having radical, so it's quite difficult experiment. And the dissociation reaction is simpler because it's just a stable molecule, relatively stable molecule hydrogen peroxide, and you just have to heat it up. And people have done it with different temperatures, with different amounts of bath gas, and they see basically a straight line dependence pretty much. So it's really just like this reaction, and you can fit it to the TROA expression. And Hong's paper combines all kinds of previous experiments, and basically they all agree about this. All right, so that's all about experiments. Now you saw how complicated they are. Maybe it makes the computation seem simpler by comparison that might have seen before. So let's go back to the computations for a second. First, how to do the computations is complicated, and the community worked out how to do it correctly from, well, there's early papers from like 1950s, but really really to do it, people maybe since 1990 or so, was a whole bunch of series of papers by all the computationalists recommending how to do each step in the calculations better and better to try to get really good accuracy. So that's what all these papers are. You see, 96, 2003, 2006, 2005, lots and lots of papers about how to do the calculations correctly. All of them, you start with the Born-Oppenheimer approximation, which is you're assuming that there's this potential V of R that we talked about before, the potential energy surface. And you will solve that using things like Gaussian or MOLPRO. And you can also use CCS-DT and DFT, and you do basis set expansions. And then we want to compute the KFTs. So remember when we were doing classical mechanics for like trying to compute the rate from cars going from New Jersey to Manhattan, that figured out we had to count the flux across it, and we had a classical expression that gives you the rate. And so we try to do the same idea for the molecules. So we divide the phase space into reactant and product region with a dividing surface. S of Q is equal to 0. The main assumption here is this Boltzmann weighting. Somebody asked a good question about that before. We're assuming that every possibility of possible positions, possible geometries, and possible motions of the atoms, they're all exactly, their probability that they occur is completely given by the Boltzmann energy, and that's it. And that's related to a thing called ergodicity. It's assuming that everything that can happen will happen equally likely, completely random. All right, so that's the starting idea. It doesn't always have to be true. Not everything is perfectly random in life, but if you start, that's actually a pretty good basis for chemistry. You can think of what's happening as you're having a trajectory, and it's trying to go from a starting point out to a product, or vice versa, from this side coming in to get stabilized. And you can write down the same equations I showed before. You can do them, we usually do them what's called canonical, where we assume everything's Boltzmann. Another way is you can assume that you have perfect energy conservation. And so all states that have exactly the same energy are equally likely to be formed, and all states with different energies have 0 probability. And then you would weight things by a delta function instead. It's called microcanonical. So those are two different ideas. And with the transition state assumptions, you end up with the formula that we saw before for the rate coefficient. And so it's a ratio of Q's, a kBT over H. And then you get this extra Boltzmann factor, and this one has to do with the definition of the 0 of energy for the Q's. So in the case we did before, we didn't have this factor because we assumed the Q's all roll in the same common 0 of energy. But in practice, when you do calculations, typically you reference each molecule to its own 0 of energy. So you consider the 0 of energy for methyl radicals to be the lowest possible energy that any methyl radical can have, the 0-point energy of methyl radical. And you don't consider the fact that you're doing a reaction of methyl radicals with O2, so the energy of O2 doesn't matter to you. So you just use the 0 of methyl. So because of that, if you use a different reference for each reactant and for each transition state, you have to have a Boltzmann factor that relates the zeros of energy to each other, and that's what this thing is here. It's the lowest V of R that's on the dividing surface, and that's also called the transition state energy, the barrier, reaction barrier. And so we can write down again the Q equations, like I showed before. And there's the picture, as we talked about before. And there's these different energies. So if we're counting the 0 of energy from the lowest 0-point energy of the reactant, and we're going up to the 0-point energy of the transition state, this thing is often called delta E00, or sometimes just delta E0. And these are the barrier height, but including the 0-point energy corrections. So it's when you have a molecule, it cannot become perfectly stationary. It's not the lowest energy state of a molecule actually has the atoms moving a little bit. And so that's called the 0-point energy. And that's this little lowest energy level that there is. And then this difference is basically what we call the delta H of reaction at 0 Kelvin. It's the energy difference between the products and the reactants, again, at the lowest achievable energies of both of them, what energy they would have at 0 Kelvin. And so these are related. So this is a really important relation, is that the forward barrier is equal to the reverse barrier plus the delta H of reaction. So they at zero Kelvin. So these have to add up. Sometimes you'll see mechanisms written where they don't satisfy this relation. That's really bad, because that's like violating the first law of thermodynamics. So they have to satisfy this relation. And it tells you if you know the delta H of reaction from the thermo, and you know the barrier in one direction, then you automatically know the barrier height in the opposite direction. All right, for bimolecular reactions, you get a slightly different formula. Instead of just 1Q over Q, you actually get this slightly different thing where it's the transition state Q divided by the volume, and then the reactant A and reactant B each divided by the volume. And these volume factors make it come out to have the units you'd expect for a bimolecular rate coefficient. So it'll become at liters per mole second would be the typical rate, or centimeters cubed per mole second, or centimeters cubed per second. Yeah.
I was wondering, in the partition function of the transition state, do you account only for the vibration in the orthogonal direction to the reaction coordinate?
Right, only the orthogonals. You don't count the reaction coordinate because we already integrated that one out to get the KBT over H came from that.
So you go along one trajectory, or you sample different trajectory, and for the bottom of the valley, do you account for vibration in both directions if there are two variables in all R?
Right. Yeah. So in the reactants here, these Qs include all of the vibrational modes. So these are typically 3n minus 6 vibrations, but this one is only 3n minus 7. It's missing one, and this KBT over H came from the analytical integral of that one.
Trajectory to go over the same point.
This formula comes from, you don't have to worry about the trajectories because we're looking only at the dividing surface. So it's like the toll gate picture of trying to figure out the rate of cars going from New Jersey to Manhattan. We don't look at what all the cars are doing everywhere in New Jersey. We only look at the ones that are right on the bridge, just about to cross into Manhattan. And we just take a photo right there and measure the velocity right there, and that's it. So we don't know anything in the story about what the molecules were doing before on their trajectory or what exactly happens afterwards. We're just looking right at we take a photo at the toll gate with a Doppler radar to see the velocity of the car, and that's it, to get our number. And the same with the molecules. So this KBT average comes from that missing coordinate from that was called the reaction coordinate that's in the transition state theory. These numbers over here are kind of confusing for people. These are called the reaction path degeneracy and the symmetry numbers of the reactants and of the transition state. These symmetry numbers have to do with, like we said, with water, if you rotate it halfway around, it looks like water again. It looks like you wouldn't be able to tell because the H atoms are indistinguishable. All H atoms are the same. You don't have one named Betty and one named Bob. They're just H. And so once you've rotated 180 degrees, it's the same thing. So that gives factors of 2s and stuff in these sigmas, depending on the exact geometries of the transition states and the reactants and products. This M is a thing called the reaction path degeneracy. Sometimes there's goofball ways that you can have two distinct transition states, but they're completely symmetry related. So sometimes you have like mirror image transition states. That the transition state is chiral. And so there's two versions of it. And that means you would get twice as much rate. And so you get a factor of 2 here. If you get it, this is kind of complicated topic about how to do this correctly, and there's several papers about it. And then these Qs are just Qs, each for themselves, and then this delta E0 is the difference between the 0-point energies of the transition state compared to the reactants. The assumption is basically that, like, just when we were considering the rate from New Jersey to Manhattan, if we measure it by measuring all the cars crossing the toll booth, we're implicitly assuming that none of them are going to do a U-turn in the middle of the George Washington Bridge and go back the other way. We think everyone that gets through our toll path is actually going to make it to Manhattan. And it's the same assumption we make with transition state theory. But in molecules, it's not always true. So some of the trajectories that get across the dividing surface actually immediately turn around and come back to the reactants. And so this turns out to be a typical maybe 50% error in the rate as computed by transition state theory compared to what actually physically happens, because a bunch of the trajectories actually do turn around. We also, both of these things lead to the fact that the transition state theory is a little bit greater than you would get from doing actual trajectories if you followed every single detail all the way through. And you can get this transition state theory number to be closer to the true value by varying the shape of the dividing surface. And the variational idea is that there's some optimal choice of dividing surface that gives the smallest possible rate, and that's actually the correct one to use, because everything you do with a wrong dividing surface increases the rate artificially. And so there's a whole version of transition state theory called variational transition state theory, where they spend a lot of time trying to adjust the dividing surfaces and see which one gives the smallest value of the rate. And Stephen Klippenstein is very famous for making a software that can do this. It's pretty tricky because the dividing surface is a hyperplane in 3n minus 6 degrees of freedom. And so there's a lot of parameters to define the dividing surface. But anyway, there's some ways to do it. All right, so why do we do this? It's because we need a lot of rate coefficients. So we have a lot of models that have 1,000 reactions or so, and we need all the numbers for all those things, and we're not going to do so many experiments, really. And often you can't perform the experiment at the actual TMP that you need for practical reasons. And so you have to do something else. And so theory, we kind of have two different ideas. One is just do correlations and interpolations without really any physical content, to just like take between the data we know and try to estimate what's in between. And the other way is really transition state theory. And there is a thing called quantum dynamics, and that actually gives you better numbers than transition state theory is really good, but it's super expensive. So you can do 4-atom systems. Actually, you can do 5-atom systems if most of the atoms are hydrogen, but that's about it. And so almost everybody now does transition state theory instead. Now, the quantum mechanics matter for the atoms, not just for the electrons. So one thing was the vibrations. The vibrational cues are really different for quantum mechanics compared to classical mechanics. So you have to include that. There's other effects, like tunneling, that are quantum mechanical. And Bill Miller wrote a series of papers that wrote the exact flux operator quantum mechanically, and then showed how you could do the exact calculation. The interesting thing about it is that you get almost the same story as transition state theory. Almost everything goes the same. And what you just see is like little tiny rounding off, because the quantum mechanics kind of smooths out some of the sharp edges you would get from classical mechanics. And then you can also try molecular dynamics. Have any of you guys ever done molecular dynamics? No? Okay, so it's a way you can try to get rates. I would say it's a really dumb way because you're trying to follow the individual trajectories. So you spend a lot of time following a trajectory around. It's like trying to figure out how many cars are going from New Jersey to Manhattan by putting a radio tracker on every car in New Jersey. And you're seeing them all drive around everywhere they go, and most of them never go to Manhattan. And so you spend a heck of a lot of time computing stuff that's not actually relevant to your rate. But it's really what happens, right? So if you really want to know what's happening to cars in New Jersey, if you put a radio tracker on every single one, you would know, right? So it's the same idea as molecular dynamics. You really know what would happen, but then the amount of computational cost is really outrageous because reactions are a low probability event. Most molecules don't react. So if you try to track what every single molecule is doing, you're mostly tracking molecules that are doing nothing. And they're just sitting there vibrating away, and at the end of the day, they're still there. And it's kind of like a little frustrating. If you want to do this, I would suggest you use the RPMD method. And my group made a program called the RPMD rate program that lets you do bimolecular reactions more accurately, including more quantum mechanics, and keep track of everything more detailed. And so you'll get slightly more accurate numbers if you do this, but it's a heck of a lot more computation. So just to warn you, if you do it, I would suggest do it for a really simple system first. You get an idea of how much computation you have to do it. So if you're willing to cope with errors of sort of factors of 2, I would say transition state theory is definitely the way to go. All right, so the way we do it, the formula is we get the Qs, we use the conventional RRHO formulas that we showed before for thermo. We use the Q trans divided by V instead of the dimensionless one. And we correct all the energies with the 0-point energy differences. And if we have a mirror image transition state, the chiral one, then we'll add another factor of 2. And then we have to work out a tunneling correction. Maybe we'll talk about that later. It's not usually so important at combustion temperatures. And so you have to find the geometry that minimizes the V of R, same as we did for thermo. Now you also have to find the geometry of the saddle point on the potential surface, on the dividing surface between the reactant and the product. And typically we do all that work with DFT calculations. Then we have to compute V of R and the second derivatives at these stationary point geometries we found as accurately as we can. Usually for the second derivatives, currently people use DFT. And usually we use the best possible method we can afford, most commonly coupled cluster, to get the single point energy of the barrier. Because the barrier height's a really important number. It comes in the exponent. It's like EA. And so if you really don't want errors in the exponent. It really makes big errors. So most commonly people would use coupled cluster. And there's other high-level methods you could try. And then you just plug all those numbers into this formula, and boom, you have a rate. More about the reaction path degeneracies. You have the rotational degeneracies pretty straightforward to figure out, as there's clear symmetry numbers for different common geometries. This thing with the optical isomers is it can be slightly confusing to figure out. And then you end up with the correction to the rate constant. And it should be what's the same as what you get from the reaction path degeneracy. If you thought about it, how many different ways can these things come together that are symmetry related? You should get the same number as you would get from this multiplication. You can check that the forward and reverse rates have to give the equilibrium constant. And so you can see if you take the ratios, you get exactly what you expect. The same thing we got for thermo. So at least this transition state theory formula is consistent with second law of thermo. All right, here's a question for you. So let's consider the reaction C6H7. Draw a picture. So C6H7 is a hexagon, and all of these carbons have a single H on them, except for one of them. So this is C6H7. And we're wondering about this spitting out one of these H atoms to go to H plus benzene. And a lot of times for benzene, we always draw it this way, just to be fun. And this one, we could draw it like double bonds here and a radical there, for example. Okay? So we're trying to do what's called a beta scission reaction, where this radical is going to make a double bond here and kick out the H. And that'll make benzene and H. And you can have the reverse, of course, that an H atom can come up to benzene and stick onto it. And this is a real species, and my students did experiments where they measure the rates of reactions of this stuff. And so this is like a real thing. And so the question is, what's the reaction? Gao, in 2009, determined the enthalpy of formation of this guy is 208. So delta H of formation equals 208 kilojoules per mole. And Sang estimated the entropy is about 375. Okay, so we know some thermo about this weird radical. And if we have an H addition, so the reverse reaction, the H here coming to, about here. So this H is coming in, and it's adding to this double bond. H additions to double bonds, the reverse reaction, EA reverse, we'd expect it to be something like 20, is that right? So what's that say? 20 kilojoules, less than or equal to 20 kilojoules per mole. Okay, at least that's from previous experience of other H atoms adding onto double bonds. And how about the Qs? What do we think the transition state looks like when you're going from here to here? Anybody have an idea? What's the geometry? If you had to guess, remember we said that you have to guess the geometries, and then the computer will optimize them from your initial guesses, but you need a good initial guess. What would be an initial guess geometry for this transition state?
One of the adjogen be further.
Okay, so the idea would be like the transition state might be like the same thing, except maybe the H, one H is far. All right, does that sound reasonable? Okay, so basically it's like looking pretty much the same except this one H is sticking out. Who knows? That'd be a guess. Seems reasonable. So because of that, you'd say, the vibrational frequencies and stuff of this and this, mostly in the geometry, the rotational moment of inertia and the mass of this are all basically the same as this, except for the vibrations that involve this H atom, which might be wildly different. But everything else should be roughly the same. So you would think that the Q for this transition state here is probably a little bit bigger than, but maybe similar to the Q of C6H7. It's a little bit bigger because the frequencies are a little bit lower. If you make the bond longer, it makes frequencies lower, and lower frequencies have higher Q. But for the translation and rotation, really nothing changes because the H atom is negligible mass compared to the rest of this, so the moment of inertia is not going to change that much. So basically the same. Is that all right? So can you figure out a lower bound on K of T? Can you think of, just from this information that you have, some lower bound on what the rate coefficient could be? This kind of calculation is super important to understand if something's reasonable. So right, the problem we get in all these computer things, you use the quantum chemistry and you get some number. Who knows if that number is reasonable or not? You need to know because the computer's not 100% reliable. So a certain percentage of the time you'll calculate it and the number you get is nonsense. You need to detect it. Yeah?
Yeah, we can use the K of H extraction from the linear inequality.
You could, yeah, you could take the, well, I guess we have it for the addition. So you could say, let's look up the K. That's a possibility. So we could try, one direction here would be to like look up what people know about reverse A's. And then somehow the forward reaction this way is somehow we related by thermo. Is that right? So that would be definitely an idea. So you could look up a reverse for similar reactions. I don't think anybody knows the true one for this particular one, but you could try. That'd definitely be a reasonable idea. That'd be one idea how to do it. Can you just do it directly from what we have? Can you figure out a lower bound just from the information we have in our hand? Any idea? Yeah.
You could calculate it with the Q that you have since it's less than the transition state Q.
Yeah, so you could go, let's see, you can go back. This is the formula, right? So what we can say is that this ratio is maybe a little bit bigger than 1. So the lower bound would just be to set this equal to 1. We know this number. And so now the only thing we're missing is the difference in the energies. Is that right? So this is what it looks like. So C6H7 is here. This is the transition state. And this is benzene plus H atom. And what we know is that the EA reverse is less than 20. So that means that this number, which is EA reverse, is less than 20 kilojoules. Or we'd expect it to be, because all the H atoms addition to double bonds are always like that. So we'd say, okay, we think this is less than 20, and we know the thermo for this guy. Is that right? So we know this is like 208. So maybe the question is, do you know what the thermo is for benzene? Do you think it's known? Yeah, right. You could look in the NIST book, web book. I'm sure it's there, right? So we get the number for this, and how about H atoms? Do we know that one? Yeah, it's definitely in the book. In fact, I even remember it. It's 52.1 kcals. See, it's we'll apply it by 4.184 kilojoules per kcal. The unit conversion. Is that right? So we know this number. I'm sure you can look up this number. So we know this energy. We know this energy. So this we know. And what did we say before? That we know the delta H of reaction, and we know the EA in one direction, we can infer the EA in the opposite direction, right? So this has to be equal to this one plus this one. Is that all right? So you can, the challenge here is to look up, so anybody here have their phone or the computer, look up what's the enthalpy formation of benzene. Okay, so 49 plus, what's this, 208? Okay. So this, and this is 208 also by coincidence. So this is This number is about 49. And this number we think is less than 20. So the maximum this could be is something about 70. All right, so this number here has got to be less than 70 kilojoules per mole. Is that all right? So now we can go back to the formula and say, okay, we know this number we can compute. We know Boltzmann's constant. We know Planck's constant. We know that this number is a little bit bigger than 1. And we know this difference in energy is 70 or less kilojoules per mole. And so you can plug them in and get a number, a lower bound on what the rate coefficient must be. Is that all right? Anyway, so this is the kind of calculation that you would do every day if you were doing actually either experiments or building kinetic models, is you want to make sure that all the numbers you're getting out from all your calculations, all your measurements actually make some sense. So you have to have some expectation of what the number should be. Yep.
How do we apply all these if we have a reaction with zero activation energy? How do we identify the transition state?
Yeah, so if you don't have any saddle point, then you don't have a transition state the way we defined it. And so you have to use a whole different theory about how to get the rate. I think I get to it a little bit later, but it's a whole different story. Yeah, if there's no barrier. Yeah. All right. Let's see. What else do we say about this? How about what are the units of K? That's another good one to check. Any idea? What units would you expect for a reaction like this, where it's this guy spitting out an H going to...
1 over second.
What?
Just 1 over second.
Yeah, just 1 over second, per second, yeah. So when you do the calculation, this thing has units of per second. And so the units should be right. This is dimensionless because these guys' Q's cancel each other out. And this is dimensionless also. The energy and energy, they cancel out. You think the reaction will follow an Arrhenius rate law? What's your thought? As far as I know, no one knows the true value because nobody ever actually measured it. So you can just make your own guess. Feel free. Do you think it will or not? Yeah.
I would say yes, because we need a certain energy to separate the hydrogen atom from the benzene ring.
Yeah, so I think that this is less than 70 kilojoules per mole. We're probably somewhere up in that range, maybe 50, 60. So it's a pretty big barrier. And this Q is not doing much. So you're not getting any really funky behavior in the T dependence from the Q. So probably it'll be pretty close to Arrhenius. I would notice that, actually, the thing to notice is that this part is the EA term in the Arrhenius, and so this first part should be the A factor, right? But notice there's a T here, and also both of these Q's have some funny T dependence. So the theory says that it should have not really be exactly Arrhenius. It should have some T dependence. And in fact, if we make Arrhenius plots and you look really carefully, you'll see they're not really straight lines. So it's close enough to a straight line that if you have bad data or you look at it funny from far away with blurry eyes, it looks like a straight line and you can use Arrhenius form. But if you look at it closely, it's not, and you don't expect it to be because there is some T dependence here. But this T dependence is very weak compared to this exponential T dependence. So that's the exponential one is what you see. All right. And then once you have the rate in one direction, you could get the rate in the reverse direction from the equilibrium constant. What you'd really need is you'd need the entropies of benzene and H. And then you could get the total delta G of reaction, therefore the Kc, therefore the relation between the forward and reverse rates. And then you can do it. And the reverse K is bimolecular, so it'll have different units. It'll have per volume, volume per second instead of per second. All right, how are we doing here? Okay, keep going. All right, so far we've only done Boltzmann. We're assuming we have a well-determined temperature. However, if you're going to handle cases like this, the whole reason why this has pressure dependence is because you're not Boltzmann. So the Boltzmann thing is obviously not right for everything. So instead, you can try to get expression called the microcanonical rate, which is how the rate depends on energy, the energy of the reactants, not on temperature. And this happens when the reactions are faster than the thermal collisions. So at low pressure conditions especially, where you can have a case where the thermalization takes a long time because it's low pressure gases. They don't exchange energy very fast. Right? We use what's the insulation in your house? Do you guys know? The insulation in your house is maybe like fiberglass bats. And what's the insulation? It's actually fiberglass is just holding the air still, so it can't convect. And basically, it's the air, it's the insulator. So air is like, gas is a very bad at thermalization. It's a very bad thermal contact. If you want thermal contact, you have like a solid copper block, right, built on your thing. That's what if you want thermal. So gases are really terrible at conducting heat, and therefore, it's pretty easy in gas phase situations to get out of Boltzmann, particularly for cases where the reactions can be really fast. And you can repeat the entire formulas for transition state theory, but don't assume Boltzmann, and instead assume that the delta function, that you have a well-defined energy. And when you do it, you end up with this crazy thing. And what this is, let's see if I can explain this. I just don't want to erase this one. Okay, erase. Here we go. Erase this guy. He's here. It's easier for you to see it over here. Jesus. So suppose you had a reaction like this. So for example, HO2 going to H plus O2. And suppose instead of doing it thermally, suppose you had some way to jump the energy up. So maybe HO2 had some absorption, and you had a special laser that had exactly the right color, so you could jump the energy of HO2 up. In reality, this is just tough because HO2 doesn't have a very convenient spectrum, but let's just go with it for a minute. Actually, I can do a different one. I'll do HCO. HCO does this. So HCO absorbs in the red. You can tune what color of red you use, and that's tuning the size of the photon that's dumping energy into HCO, and then you form HCO with that much energy, and it will make, if you go above the dissociation limit, it will go and make H plus CO. All right? Because we prepared the HCO with exactly a known amount of energy, because we used spectroscopy to make exactly this one. So that's the only energy we got. We don't have any HCO with energy here. We don't have any HCO with energy here, because this is not Boltzmann. This is just pure energy. We maybe have a vacuum. We squirt one HCO molecule in it. We shoot it with a laser beam. Boom, it's got that much energy. Okay? So now we want to know, what is the rate? How fast does this fall apart to make H plus CO? That's the question. What's this K? This would be the K of E. And the formula for it is that we should count up how many energy states there are over here, and this number is called N of E, or N double dagger of E. And that's the formula up there, N special double dagger of E. And in the formula, there's a Planck's constant, and then there's one more thing, rho react. And what that is that I put this much energy in, but actually there's several energy states, different quantum states of H2O that have essentially the same energy. And if I take the number of these states, the number of HCO energies, and I kind of divide them by the delta E, maybe it's the width of the photon energy, the uncertainty of the photon energy. This thing would be rho of E. So I add up how many of these guys there are over this span, little span delta E, and I get a thing that's called the density of states. How many states there are per unit energy of HCO. And if I take the ratio of this number, which is how many states there are up to this energy, and this number, which is how many states there are per energy, and Planck's constant, it turns out that that's the rate coefficient for falling apart. And so this is a kind of weird looking formula. And it was proposed by Rudy Marcus, who later got the Nobel Prize, like 1959 or something like that, 1950s, when he was assistant professor. And a lot of people didn't believe it. And so fast forward to like 1988, 89, it's still a big controversy. So it's like 30 years later, nobody knows because there was no way to experimentally measure it with the apparatus they had in the 1950s. And there were some other theories that also matched basically all the experiments as well as they could tell. Yeah?
Part of the you account also for translational stage?
You have to
because the volume is going to make a change.
You should count the states that satisfy the conservation laws. So you count that if this is like a stationary HCO, then you count all the states that have H and CO counterbalance so that the center of mass stays constant.
So no translation.
Yeah. And then rotation also, you should have the total, how much this is rotating, has a certain angular momentum. And so you should add up all the states of these guys that have angular momentum that matches this number.
So the volume is not affected.
Yeah. And this formula that Marcus proposed, that he called the RKM formula, if you look back in the 1930s, Wigner wrote a really nice paper, and basically in classical StatMech you would get the same formula. And Wigner basically had it, but he didn't really advertise it because he was totally interested in the Boltzmann case. So he just kind of wrote it down without saying much. When you do well, what does this imply? So if I change the energy, say to some new energy here, there'll be a slightly different density of states because at higher energy there's more states. So there'll be some different rho, but there'll be a wildly different n because now I'm going to add all these states and all these extra ones too, all the way up to this new energy. So this would say that this, if I use this higher photon, it was like more to the green instead of the yellow instead of the red, then the HCO would fall apart much faster because this n would be much larger. That's the idea. So the question is that true? Or what would that imply? And what it would imply is that, what can I do here? Here we go. If I make a plot of the K of E versus the E, there should be some E that's right at the dissociation limit, and below that E, I won't get any reaction because I don't have enough energy. So it should start at 0. This should be the threshold. And then it should go up. And initially, right at the threshold, there'll just be one quantum state, the lowest one. So I'll have no 0 rate, and then boom, I'll have the rate that corresponds to n equals 1. And then as I go up, every time I get enough energy to get another quantum state, when I get to the second quantum state, I'll have another step. So it'll jump up to n equals 2. Does that make sense? Yeah. And then this will keep going like this, a staircase kind of thing. And it goes down a little bit each time because the rho keeps increasing with energy. So these are not perfectly flat, but basically like this with these steps. Like that. This is the prediction of the theory of RCAM. Bill Miller went back and said, let's put the quantum mechanical effects in. And when I put the quantum mechanical effects, it looks just the same, except you get a little bit of possibility of reaction when you don't have quite enough energy because of some magic of quantum mechanics. And you have a little bit less reaction here because you can have things reflect in quantum mechanics. So things that should be allowed to happen can't happen. And then you get a little bit more tunneling here, like this. And so the whole thing looks the same, but kind of smoothed out. So that's the quantum mechanical version, but basically the same. It looks the same. It's kind of bumpy. It looks like a staircase. When you do the experiment, this is what you see. This is exactly what you see. You see these bumps, and they match up to the energy levels of this level over here. And I know it because I did the experiment when I was a graduate student. That was I mentioned in the lunch that I got a lucky experiment on my second one after I had the horrible year. And this was it. We turned on the thing, we scanned the color of the laser, and we saw these weird stuff where it went up and down like that. And it turned out this was just this. It was the first time it had been clearly observed. Yeah, so sometimes you're lucky. Here it is. So this is the measurement we made, 1988. Made it with Yichai Chen and Brad Moore's lab. And that's the KV, basically. It's a quantity that's proportional to KV. And the scatter stuff is the noise in our measurements. So this is pretty convincing that is actually correct. Then after us, Zoel, he measured the rates more directly. We had to use an indirect way of doing it in our experiment. And so that was very directly verified. The RCAM formula is correct. And so then Zoel got the Nobel Prize for that. And now everybody believes it. And you can take the Boltzmann average of this thing, and it comes back to what you expect. So this is perfectly consistent with the regular transition theory Boltzmann version. And you get extra facts out of this, like the if I have a isomerization reaction, A and B, if I can compute the K of E here, and I know the density of states here, then I can do the same thing on this side, and the K, and the product of the K of E times rho of E, that the product of rho times K in this direction has to equal rho times K in that direction. It's called detailed balance. And that turns out to be very convenient for some calculations to know that's a real true thing. All right, let's take another break.